players choose this action together. Okay? And what is the probability for that event? Probability of that event is this. Okay? So this is probability that A minus I is actually chosen when all other players play sigma minus I. Okay? So this is the notation we introduced last week. Okay, so of course, there are possibly a number of different actions you can plug to this place, right? So you have to add up all these kind of payoffs across all possible A minus 1 I. Okay? If you add up everything, then that's exactly equals the payoff of player I. Okay? So we would like to calculate what is expected payoff when player I plays this strategy and all other players plays this strategy. Okay? Is it clear first of all? So this means the payoff for player I when I place these strategies and when the other player plays this strategy. Okay? And what is this? This is payoff when player I plays sigma I, so the same strategies, but it turns out that the other player's actual choice is sigma minus I. Okay? So that is the case, the other player's action is sigma minus I with this probability. Okay? And there can be many other possible actions you can plug to here and here. So if you add up all of these kind of things, that is exactly equals to expected payoff. Okay? So for example, because some of you seem confused, so let's think about prisoner's dilemma game. Okay? So we would like to calculate player I's payoff when I play sigma 1 and when the other play sigma 2. Okay? Or sigma minus 1. Okay? So there are two actions that player 2 actually can choose, C and D. So with this probability, player 2 will choose C. In that case, what is player 1's payoff? Player 1's payoff will be sigma 1 and C. Okay? Plus, with the other probability, sigma minus 1D, player 2 will choose D. Okay? Conditioning on that event, player 1's payoff will be this one. Okay? Basically, we do exactly the same thing here. Okay? So, notation here is a little bit more general or a little bit more abstract, but basically what we do here is exactly this thing. Okay? Okay, so that explains why we have these equations here. And we can do the same thing for sigma I prime. Okay? And you can see here, okay, so let's compare these two things. You can see exactly same sigma minus I, A minus I here, and exactly same sigma minus I, A minus I here. Okay? But we assume that the second term here, UI term, this one is strictly larger than the other thing here, the other term here, for any A minus I. Okay? So that is our assumption. We assume this thing. So this thing is true for any A minus I, which means that the term here, UI term here, in the first line, is strictly larger than UI term here in the second line. Okay? And we have exactly same sigma minus I here, sigma minus I terms here. So that explains, the first line here is strictly larger than the second line. Okay? And that shows that actually, if this is true for any a minus I, actually inequality also holds for any sigma minus I. So that shows that, in this case, sigma I actually strictly dominates sigma I prime. Okay? So I kind of, went through all details of this proof for two purposes. First of all, it's kind of used for lemma, right? I mean, in order to check whether one is strictly dominating the other one, you have to check all sigma minus I. But this lemma simplifies, the thing we have to check kind of dramatically, right? So this is really useful lemma when actually you have to solve a game with the method we just presented. So that's the reason I had to go through all details. Basically it is useful. And the other thing is that I also, hope that, following me here, you kind of get yourself familiar to this kind of calculation. So this kind of calculation of expected payoff, that's something like, you have to do all the time throughout this lesson. Okay? I give you a strategy, then you have to calculate what is payoff. Okay, so this is really useful lemma. And we have another lemma here. This says that, let's say, a pure strategy AI tilde here. So we have kind of, wavy symbol above AI. So I call that AI tilde. So this is strictly dominated by, let's say, AI tilde prime. Okay? So this is AI tilde prime is better strategy than AI tilde. Then any mixed strategy sigma I such that AI prime is in the support of sigma I is also strictly dominated by some strategy. Okay, what does it mean? So here, first of all, support of a mixed strategy, that is the set of all actions which is chosen with positive probability. Okay? Let's say, let's come back to example of prisoner's dilemma. Let's say player 1 chooses C with probability 1/2, D with probability 1/2. So in that case, the support of his or her strategy is C and D. Okay? Let's say player 1 chooses C with probability 0.99 and D with probability 0.01. Then still the support is C and D. Okay? Because both actions are chosen with positive probability. But if player 1 chooses C with probability 1, then support is just C. Okay, so that is what I mean by support. Okay, so what does it mean here? So what does it say then? Okay, it says that if one action is strictly dominated by some strategy, okay? So which means that, in that case, you can say that if this guy is rational, AI tilde is never played. Okay, AI tilde is never played because it is strictly dominated by AI tilde prime. Okay, so that's kind of something we can see immediately. But this lemma says that, moreover, any mixed strategy which chooses AI tilde with positive probability, that kind of strategy is also never played. Okay. So coming back to our prisoner's dilemma again, so on the very first slides here, we showed that C is strictly dominated by D. Okay? So C is strictly dominated by D. That means player 1 never chooses C if he is rational. But if you apply this lemma, then you can say that, immediately you can say that not only the pure strategy C, but any mixed strategies that chooses C with positive probabilities, that kind of mixed strategies also never play. Okay? So applying this lemma, you can immediately say that here, even without going through this kind of calculation, you actually could immediately say that player 1 and 2, they always have to play D. Because all strategies that assigns positive probability to C, all those kind of strategies are strictly dominated by some strategy. So the only remaining reasonable strategy is D for those players. Okay? So I'm not gonna really go details of this proof. Basically, you kind of prove in the same way actually. I mean, you first, calculate sigma ui, sigma I, and sigma minus I. So if you calculate these things, then it's actually clear that this inequality is always true. I mean, I just will leave it as your exercise. Proof is kind of easy here. Once you get familiar to calculation of expected field. Okay? Okay, so now for next 10 minutes, let's apply these two lemmas to solve a little bit more complicated game. Okay? So prisoner's dilemma was nice game, it was really simple. But let's try some more complicated one. So this is now really interesting game actually, to be honest. So this is another boring example. Let's say player 1 and player 2, they have 3 actions. Player 1 has U for up, C for center, D for down. Okay, so he or she has 3 actions, U, C, D. And player 2 also has 3 actions, L, M, R. L for left, M for middle, R for right. Okay? Okay, so and when we solve this problem game together, we're gonna also use our assumption that it is common knowledge that all players are ready. Okay, we're gonna solve this problem using that assumption, commonality of rationality, and the notion of strictly dominating strategy, and 2 lemmas. Okay, so first of all, you can see here. As you can see, read here, M strictly dominates R. Why? Okay, so basically, in order to show that M strictly dominates R, okay, so M strictly dominates R, so we write this is my claim. So how to prove it? So we're gonna use the first lemma. This lemma, okay, to show this. So in order to show this, we have to show. So this is player 2, and A1 M. So this is player 1's action, and this is player 2's action. Is strictly larger than if you show that, that means, as long as player 1 plays pure strategies only, and always gives strictly better payoff than R. Okay? So first of all, you have to understand that it does not really automatically means, it does not automatically mean M dominates R. Right? Because, in order to say that M strictly dominates R, you have to check all mixed strategies, not only pure strategies. Okay? But thanks to our first lemma, here, you don't really have to check all mixed strategies of player 1. As long as this is true for pure strategies, all pure strategies of player 1, you can say that M strictly dominates R. Okay, so we are talking about player 2's rationality here. Okay? Okay, and indeed that's true, right? So we are comparing M and R. So if player 1 chooses U, then M gives 2 to player 2, R gives 1 to player 2. So M is better than R. If player 1 chooses U, if player 1 chooses C, then again, so the second numbers are player 2's payoff. So M gives payoff equal to 2 to player 2, but R gives 0. So M is again better than R. Even if player 1 chooses D, 2 is better than 0, so again M dominates R. Okay? So this inequality is true for any pure strategy of player 1. Okay? So we can say that using this lemma, actually M is better than R. Always. Even if player 1 randomizes. Okay? Okay, then how can we use this fact? Okay, so we know that, remember that player 2 is rational. Okay? And moreover, it is common knowledge. Which means that both players, not only player 2, but player 1 also understand that player 2 will never use R. Player R, strategy R here, pure strategy R is always worse strategy than M. So player 2 has to, player 2 never uses R. That's clear, right? And moreover, player 1 also understands that player 2 is rational. Which means that player 1 also understands that player 2 will never use R. Okay? So which means that, okay, so it is common knowledge that player 2 is rational, then you can delete R. R is never used in this game, and all players understand that. So there is no really reason we have to consider R in this game. Okay? It is kind of dummy. It is never used. So you can just, straightly delete R from the table. There is no loss in that. Okay, so let me actually duplicate, so we have 3 actions. Okay, so M strictly dominates R, so you can just delete this column. It is never used. Okay? Okay, then once you delete R, then you can actually see, after you delete R, you can say actually more. Okay, so it is never played, so let's ignore this part of the table. Then now you can see U is, after delete this part, U dominates C and D. We are talking about player 1 now. So here 1 is larger than 0, 0. And here 1 is also larger than 0, 0. Okay? So player 1's strategy U dominates C and D. Okay? So you can delete C and D as well. Okay, so it seems very easy, very trivial, but actually this is really deep observation. Why we could delete C and D. Mathematically, it's very easy exercise, but in terms of idea behind it, actually this is really deep observation. So this is the place you use the assumption of common knowledge. Okay? Okay, so to see that, let's say, let's look at the table as it is. Before you deleted R, you could not say U dominates C, for example. Why? Because if player 2 chooses R, then payoff from choosing U is 0, but payoff from choosing C is 2. Okay? So I'm comparing these two numbers. Here you can see 0 here and 2 here. Okay? So if player 2 chooses R, then actually C is better than U in player 1's perspective. Okay? So, however, player 1 knows player 2 is rational. Okay? So, player 1 could delete C. Okay, so technically speaking, strictly speaking, U does not dominate C. Right? Because of the possibility of player 2 choosing R. Right? So technically speaking, U does not strictly dominate C. But U dominates C only after player 1 deletes R from the table. Okay? And the reason that player 1 could delete R was player 1 knows player 2 is rational. Okay? So that's the reason we could C and D from the table as well. Okay, then you can do more. If M is better than L for player 2. Once you reach this point, you can see M is better than L in player 2's point of view. So you can delete L as well. Okay? So here you use the power of the assumption of common knowledge here. Okay, again, M does not dominate L, strictly speaking, because what if player 1 chooses C? Then L and M, both of them provide payoff equal to 2. So they are even, right? So in that sense, M does not dominate L. If player 1 chooses C, M and L and M, they are equally good. So M does not dominate L. But M dominates L only if player 1 deletes C and D. Right? So, and the reason that player 1 could delete C and D was player 1 knows player 2 is rational. So when you delete L, what you really use here is player 2 knows player 1 knows player 2 is rational. Okay? Only after you use that assumption, you could erase L. Player 2 knows, player 1 knows, player 1 is rational. I'm sorry, player 2 is rational. So that's basically the idea behind this. So UM is the only rationalizable outcome. All rational players will eventually play UNM. So that's the only rational outcome or rationalizable outcome. So this kind of process, deletion of strictly dominated strategies in steps, we call that the process of iterated elimination of strictly dominated strategies. Okay? So mathematically, it's kind of easy actually. You compare numbers on the table, and you delete some strategies whenever you think, whenever you can find a better pure strategy. Okay? Okay, so another example. So in the second example, we have very similar, almost identical table, but except that we have two here. So the outcome UL generates payoff 1 and 2, where it was 1 and 0 in the previous. It was 1 and 0 here, but in the next example it is 1 and 2. Okay? So we have the same, almost the same example, but we have two. So let's try to apply the same idea. Again, M dominates R, right? So there is nothing really changing for this column and this column. So M still dominates R, so which means that you can still delete R here. Okay? And after you delete R, you can see U is better than C and D. So 1 is better than 0, 0, 1 is better than 0, 0. You can ignore this part of the table, so U is better than C and D. Okay? So you can erase this line and this row as well. And then that's it. There is nothing more you can do. So here we have two outcomes, UL and UM, and most of them are rationalized. Okay, the last example is rock, scissors, and paper. You can, actually, it is not really easy, but believe me, there is no strictly dominated strategies here. Actually, it's not really that difficult. Okay, so let's check whether let's focus on player 1 for now. R is never strictly dominated by any strategy. Why? Because let's say player 1, for some reason, let's say player 1 believes player 2 will choose scissors. Then R is always, then R is the best strategy for player 1. Okay, so R is better than scissors, R is better than papers, actually R is better than all other mixed strategies. Okay, so under the belief that player 2 will choose scissors for sure, R is the best response of player 1, the best thing that player 1 can choose, which means that R is never strictly dominated by any strategy. Okay? Similarly, S is never strictly dominated. Paper is also never strictly dominated. And player 2 also, for player 2, we can also see that no strategies, no actions among three actions, round, scissors, and paper. All these three pure strategies, all of them are never dominated by other strategies, by some strategy. Okay? So which means that even if you try to apply the same idea here for this game, there is no column or no row you can erase. Which means that all 9 outcomes, they are rationalized. Okay? So I also have some references here if you need some reading material. If you want to go into more deeply here and read this chapter. Okay, so what does this example really tell us? Okay. First of all, okay, so our conclusion here is all 9 outcomes are rationalizable. Relying on common knowledge of rationality, we could not erase any single outcome. Okay? So this is really disappointing result. First of all. Okay, let's say so I don't know. I'm kind of professor in economic department, and everyone knows that I'm specialized in game theory. And some people come to me then ask me, what is your theory is telling about draft figures and papers. And let's say, okay, so obviously my answer is that everything can be the case. That is really disappointing, right? So when this guy asked me about draft figures and paper, probably he expected some more specific answer, right? Let's say some outcome is better than the other outcome, or something like that. But it turns out that we could not say it. Okay, for now, I mean, all 9 outcomes are just equally good. So in that sense, this is very disappointing observation. Okay. Okay, so that is the first comment I'd like to say here. I would like to make here. Okay. But if you think very carefully what's really going on here, there is something very strange here. Okay, let's focus on the outcome RS. Okay, let's focus on the outcome RS. Okay, so RS is rationalizable outcome in the sense we just discussed. Okay, so first of all, player 1 can rationalize R, his or her choice of R, by saying that, okay, I believe for some reason, I expect player 2 will choose S. Okay, let's say player 1 says that for some reason, I believe player 2 will choose S. So that expectation of mine, this is my expectation, do not ask what, where it comes from. This is my expectation, and under this expectation, R is my best choice. Okay? So player 1 can rationalize R in that way. Okay, that's okay. But let's ask exactly the same question to player 2. Then player 2 can say something like this. Okay, S is my best choice under the expectation that player 1 will choose P. Okay? Let's do the same exercise. Let's ask exactly the same question for the outcome RR. Okay? Okay, so player 1 is again asked why he will or she will choose R. Then he can or she can say that the other player will choose S. That's my expectation. Okay? So if player 2 chooses S, R is my best option, best choice. And player 2 can answer exactly the same. Okay, so what's wrong really about this argument here? Okay, player 1 expects player 2 will play S. But what actually player 2 plays is R. Okay? Which means that, to defend or rationalize his or her choice, player 1 has to make up some expectation, some belief, but that belief is not really true. It's incorrect belief, actually. And player 2 also had to make up a incorrect belief about the other guy's choice. Okay? Okay, so let's say they defend their choices in this way, and they actually, are matched with each other and play. Then they will immediately find that their expectations were incorrect. Okay? So here the problem is, you can rationalize R and R with some belief about the other guy's choices, but that belief is incorrect belief. And let's say you repeat this game again and again, okay? Then you will find out very easily, actually immediately, you will find out your expectation is incorrect. Okay, then what player one has to do is, okay, so now I have to revise my belief. And player 2 also have to revise his or her belief. Okay? So that's the problem of this outcome. So okay, so in economics, we usually focus on the concept of equilibrium, right? So all of you took advanced microeconomics, so I believe you have at least a rough idea about what equilibrium is. Okay? So in equilibrium, there should be no movement anymore. I mean, if the situation gets into a equilibrium, then there is no reason to move, right? For any players. But that's clearly not true for RR. Once you reach to RR, let's say, but you will find out that your expectation was not really correct. So you have to revise your expectation further. So that's clearly not expectation. That's clearly not an equilibrium. Okay? So that's what I'm against about this outcome right now. Okay? And actually, especially for this game, you know what is kind of rational expectation. You know that if you are randomly matched with one of your classmates here, let's say you have to play with that guy, your match, this game together, then you have probably most of you believe that the other guy will randomize roughly the same case with equal probability. And that is actually, we know that is actually correct expectation. Okay? So the problem of this procedure, it has a really long name. So iterative elimination of strictly dominated strategies. So this procedure, is cool, but sometimes it produces some unsatisfactory outcome. Okay? So that requires us to think about, how we can sharpen our theory further to narrow down, what is our prediction about this game. Okay? So that is our next question, next topic. Any questions so far? Okay, let me briefly wrap up. So we define strict strategic dominance. So let's say player sigma I is strictly dominated by sigma I prime. That means sigma I is never strict. Okay? So that's the idea here. And using that idea together with the idea of common knowledge of rationality, we could iteratively erase some actions from the game. And sometimes it gives you very specific prediction. So in this example, in the first example here, we could see that after this procedure of elimination of actions, UM is the only rationalizable outcome. So this is kind of a good example. But sometimes we have multiple outcomes. Even worse, sometimes we could not isolate any outcome. And the problem about this kind of example, for example here, Roxidus and taper is, okay, so some actions are rationalizable, some of them survive our elimination procedure, but they have some problem in terms of incorrect expectation over the other players. Okay, so that is just quick summary. Okay, so then let's have 10 minutes break until